Hey guys, so I'm Tyler, Sorey. The talk is on GPU programming and how we can apply it to robotics to make things better. So I guess, should I start with my work or just jump right into it?
Jump right in directly.
Cool. So as a quick overview, GPU programming is programming on the graphics processing unit. The common thought for GPUs is that they're used for image rendering, but with the newer GPUs, we can use them for computations as well, and they're really good at it. So not all problems can be parallelized well. You can actually see slowdown doing the wrong problem. Some of these, we'll go over them later, but things where like a Kalman filter or graph algorithms, things where we don't know the next step until we complete the current step, those sorts of algorithms are not going to work well on a GPU. Some of the things that work well are going to be computer vision algorithms, image processing, stuff like that, because we can do all of it at the same time without needing to know a prior step. It's generally more difficult to program on a GPU for people just because it's hard to think in those terms in that kind of a multi-threaded environment, because you'll have thousands of threads running all at the same time doing something, and that becomes difficult, but it just takes a little bit of practice. So why do we like cores? The new Ryzen chips from AMD have like 16 hyper-threaded, or what they're calling it, similar to Intel has 8. Whereas a new 1080 like this one has like 3,000, 3584. You got 11 gigs of RAM on it, so you can pretty much copy anything you need to it instead of having to do multiple copies. And the clock speeds is slower, but because of the cores, you still have a huge performance gain. Once again, as I said, multitasking is way better than a CPU just because of the number of cores, which makes them great for image processing. Depending on the algorithm that you use, obviously you're going to see different speedups. We'll see one at the end with some great results. So many of the problems we face in robotics today are going to be computer vision related, which are highly parallelizable. Some of this is going to be mapping, navigation, object detection, object tracking. All of these sorts of things are going to be highly computer vision based, camera based, and that makes them great candidates for parallelization, GPU programming. And so it's like a double win really, because there are a lot of things that aren't parallelizable on a CPU, and because we can free up some of the CPU resources onto and offload that onto the GPU, that allows for more efficient CPU processing as well. Object tracking and things like that in robotics is going to be helpful because the faster that we can know something, the more accurately that we can know something, the better, the safer the flight can be, things like that, the better the information we get from it can be. And with modern advancements, they're very likely. The 1080 won't fit on a drone very well, but this is a developer board, but this right here is the TX2 that you see here. And so they've come a long way in weight, in terms of weight, power consumption, while still delivering 256 cores with 8 gigs of RAM. And that's huge. That really made it possible for a drone where weight is so important and power supply can't be huge. So with GPU programming, because it's such a crucial tool nowadays, there's a lot of helpful tools that people have developed to come out with it. Like NVIDIA has come out with CUDA, and Thrust has been built on top of it. CUDA gives you a really nice like C-like interface to the GPU, which is really helpful because before it was very difficult to try and actually program on it efficiently. Thrust is even better. It sits on top of CUDA, and it gives you a C++ feel. And here's a small code snippet. I don't know if you can see it all the way back here, but this is Thrust code. And so as you can see, it looks just like C++. The difference is that you have to use the Thrust namespace in it. It just makes it a lot easier and a lot quicker to develop parallelized algorithms. Does anybody have any questions about tools or anything like that?
So just curious, NVIDIA is probably leading company in the GPU world. AMD is also the
Yeah, NVIDIA would definitely be the leading for GPU, general processing on a GPU. AMD's cards are great, but you could use something like OpenCL. There are tools to code on AMD cards, but NVIDIA has really taken a stand by creating CUDA and making it so easy and so well known to code on their cards that it's really become the leader in computation.
Tyler, could you comment about how efficiently you can program given that you are programming on top of the functionalities that something like Thrust provides?
How efficiently compared to just straight C++?
Right.
You're not going to see a lot of overhead from using Thrust. The main overhead that you receive when you're coding on a GPU is going to be the copying to and from the device that need to happen now. In Thrust, they happen behind the scenes, so you don't actually see that in the code. If you're using CUDA, you would have to do that manually, but that's really where your main overhead is going to be. You'll have to copy all your vectors, everything you want to compute to the GPU, do your computations, and then copy it all back, and that's overhead that you wouldn't have on a CPU.
So does Thrust do anything to optimize that? Like, I mean, if you were to program it manually, is it likely that you would program it slower than the Thrust does, or is it pretty much the same?
It uses the CUDA. Thrust uses the CUDA interface behind the scenes.
Yeah.
So if you were to use the CUDA interface, you wouldn't. Yeah, it would be hard. You're not going to gain a lot by using Thrust.
Okay.
They haven't really optimized CUDA at all. They've just built on top of it.
Okay.
It just makes the code a lot cleaner when you use a higher level. So there are also a ton of pre-built things to make programming even simpler. So we have libraries like OpenCV. You may have used those for computer vision. They also have a GPU implementations for a lot of their algorithms, which makes life even easier for the programmer. VisionWorks, they have a lot of algorithms already pre-built for you. They do things in image arithmetic, flow and depth, geometric transformations, filters, features, analysis at the end. And it really helps because it's just pre-built for you and it's well tested, generally. There's also Google Cloud Machine Services, machine learning services. So if you wanted to apply your GPU programming to machine learning, Google's got a great cloud service for you, so you don't have to necessarily have the hardware. You can offload it all onto the cloud, and it'll do that computation for you. There's something called TensorFlow, which is a great neural network library as well. And it offers a lot of pre-built things for you. So GPU programming really isn't as scary as it seems at first glance. It used to be, and that seems to be the thought process with it. The hardest part is thinking it multi-threaded, but here's an example of just a very simple example of a C++ versus a CUDA implementation of vector addition. So the cool part is that over here, don't judge the code, but you would pass it. The only reason you shouldn't use output parameters, but I just wanted to make it the same as the vector addition used on CUDA. And so what you would do is you pass it, and then you'd iterate through your list of 10,000 and add them all sequentially. Not too great. But over here, so this keyword global just means that this is a CUDA kernel. It's going to run on the GPU. And that's signifying to CUDA that this is meant to run on the GPU. And then you're going to pass it vectors. Now, once again, as I was saying with the memory, you do have to allocate memory on the GPU as well as on the CPU, on the hardware, on the CPU. So that I guess is another overhead that you do have with GPU programming. But once you do, you would allocate the memory on the GPU, transfer your information to the GPU memory allocated, and then run your computations. So this is just a way to signify the thread. You don't want threads to step on each other or do the same data twice or anything like that. So that's what thread ID, that's all built into CUDA. And then you would just do your addition the same way. So it's very similar to C++. It feels like C++, and Thrust would make it even nicer looking. But this would be in main. This is the copying that I was talking about. So you would copy each from the host to the device, and then do your addition, and then copy it back. So this syntax is really the extra that you're going to see in main when you call it. So these triple angle brackets, what these signify is how many blocks and threads you want to run. So the threads are per block, and the blocks are a logical thing. There is a maximum number of threads per block, and that's hardware dependent. So you have to figure that out for the specific hardware you're coding on. But once you do, the threads also get to utilize shared memory within the block, and then they can also synchronize threads inter-block, which is really helpful for things like image processing. And we'll see that in a second. So this is a Sobel filter, a little more complex. And what the Sobel filter does here isn't super important for what we're trying to learn here. But once again, the global keyword is just an indication that it's a kernel running on the GPU, not on the CPU. These block dimensions and thread IDs, those are once again to ensure that threads aren't stepping on each other's memory or doing the same computations twice. And then local block is a shared memory on the device. just so that's not a keyword, it's defined. And then sync threads. So we'll see this down at the bottom. This is what I was talking about with interblock syncing. So what they'll do is they'll run through all this computation on the image itself. They'll want to sync the threads and then start another set of computations that's on the next slide on the same image. So you want to sync the threads in between to make sure, so this is a blocking call for all threads. Thread 1 may get here, but it may take a second or however long for the nth thread to get there. But they will all wait at sync threads until they've all gotten there, and then continue through the next step of computations. Once again, I know the code's kind of overbearing, but it's a good example of how to use a lot of the things that are on it. And so what you go through is you eventually want to compute the Sobel, which is just a mask, 3x3 mask with the image. But this is all done in parallel, and I know that's hard to think about. It's much easier to think about running this in a loop or running over like an n-squared algorithm to iterate over the image and then iterate over the mask, so you'd have an n-squared, k-squared algorithm. But this can actually do a lot of that in parallel, depending on your image size and your hardware. So the issue is that with the older hardware, with the hardware we see here, with the lesser cores, you can only, you're only going to be able to run 256 things at once because there are only 256 cores. Way better than a CPU still, but not nearly as good as the 3000 they have on a 1080. So when we look at the results, we'll talk about that a little bit. So here's the results of just the Sobel filter. Everyone tends to have pictures, so I figured I'd put one up. Just looks cool. That's Lena, very well-known computer vision image. And so here's some results that I found. So this was actually using OpenCL, which is a nice tool to use if you want it to be. OpenCL gives you the ability to not only run your code just on the CPU if you don't have a GPU present on the machine it's running on the GPU if it is present, and on an NVIDIA or an AMD GPU. So that's what's nice about OpenCL. Is it's very, it's able to go kind of whichever way. But this was run with an Intel i7 and an NVIDIA GTX 470. So the 470 isn't a great card, not nearly as good as the ones today. One of the key factors is the less cores and the less onboard memory compared to like a 1080. But we're still seeing speedups of 1600 times on the GPU for a 512 by 512 image. It goes down, which is kind of counterproductive. You'd think the larger the image, the more chance you have to parallelize it. But once again, that's hardware constricted because of the number of cores. Now, if you were to run this on something like a 1080, you'd probably see better speedups as we got larger in the images, to a point. Once again, I mean, you're still seeing a 200 times speedup, but that's kind of how that goes. And here's the reference, in case anybody wants to see it, for where you can read the paper on a little bit deeper into this. So some neat places that are using CUDA. It's well known now. It's widely used because of the ability to efficiently program in it and the speed up that you receive from it. So Harvard, they're using it a lot. There's this guy, Chris Secca, and he's using it for computational mathematics. The n-body problem is a very common one to be used for this because each body can be computed individually. So that's kind of what they're doing, generalized n-body problems. At MIT, Mark Bath is using it for biomolecular engineering, DNA, stuff like that. So bioinformatics is a heavy field for this as well. Ian Lane, totally forgot the school on that one. That's CMU. So Carnegie Mellon University, Ian Lane is using it for speech recognition, image processing, natural language processing. These are all algorithms that really lend themselves to parallelization. You can see slowdowns on things like sorting algorithms because they are so deterministic on the step before, which is really hurtful. So if you have to wait, it doesn't help you because the cores on a CPU are going to be stronger. Less of them though. And if you want more information, CUDA's got a spotlight for each of the major universities using it. Some learning resources. NVIDIA also, as well as putting out CUDA, puts out a lot of information to help you kind of pick up GPU programming. From Learn by Example. So if you learn by examples, this is a great reference. It's a book. It goes through very simple to very complex examples. They've got the toolkit documentation, so that's just the CUDA documentation. And that's also really nice. I would recommend going through the examples first so you kind of get a feel for it. And then there's also online courses that are free, Udacity. Those are offered through NVIDIA to learn GPU programming. If anybody wants a picture of the slides, I think we can get that for you guys. So, do we have any questions? Was that helpful a little bit?
Yeah, great. It's a great introduction. Thank you.
Cool. Well,
In what way, you mentioned sorting might slow it down.
Mhm.
I would think that there would be sorting, but is there no sorting or reduced sorting in the robotics, or?
So what I was talking about mostly was that sorting algorithms, some of them are deterministic on the step. If you're on the nth step, the n+1 step is dependent on the nth step, which means that you won't see a speed up by parallelizing it. Because even if you've got multiple threads trying to do this, this thread has to wait for this thread to finish still. And so that kind of hurts that. There are sorting algorithms, some out there that use like divide and conquer tactics, but and there are some sorting algorithms that are parallelizable, but generally deterministic algorithms like that or unpredictable algorithms are very hard to see any sort of speed up on.